Have you ever wondered how we predict rainfall patterns, stock market trends, or even lifespans of devices? This involves continuous random variables. Hi everyone, welcome to this presentation where we'll be diving into the fascinating world of continuous random variables, focusing on two key concepts, the probability density function and the cumulative distribution function. We'll cover their definitions, key assumptions, and how they work together to help us understand probabilities for continuous data. By the end of this video, you'll not only understand what PDF and CDF mean, but also why they're so important in the fields like data science, economics, and everyday decision making. Let's get started.
Let's take a quick look at today's lesson outline. This will guide us through the key concepts we'll cover step by step. First, we'll start by understanding the concept of a continuous random variable. This is the foundation of everything we'll discuss today. Next, we'll explore the probability density function, or PDF. We'll discuss what it represents and how it works. Then we'll move on to the cumulative distribution function, or CDF. We'll explain how these two concepts are connected and why the CDF is so useful. And finally, we'll put theory into practice by solving problems. We'll compute probabilities using PDFs and CDFs, giving you hands-on experience to solidify your understanding. What is a continuous random variable? Continuous random variables, these are variables that can take on any value within a range. Think of something like temperature or weight. It's not limited to whole numbers but can be any value like 37.5 degrees Celsius or 2.8 kilograms. Example: compare this to rolling a die, which is a discrete random variable. A die can only land on 1, 2, 3, 4, 5, or 6, nothing in between. But if you measure the height of a boy, you could get values like 121.1 centimeters, 123.12 centimeters, or 125.123 centimeters.
When computing probabilities for discrete random variables, we usually substitute the value of the random variable into a formula. However, this is not the same for continuous variables since they can take up infinite values within an interval.
So what is probability density function?
A probability density function is a mathematical function used to describe probabilities of a continuous random variable. Continuous random variables have an infinite number of possible values, like any value in a real interval. Example: height, weight, time. Main points are rules of probability density functions. Rule number 1.
The total area under the curve of the function must be equal to 1. This represents the idea that the sum of all probabilities for the random variable is 100%. Rule number 2. The height of the function, or the value of the PDF, must always be greater than or equal to 0 for any possible value of the random variable. This is because probabilities can't be negative. Unlike discrete variables where probabilities are assigned to individual points, the PDF assigns probabilities over intervals. You can think of this as measuring probabilities for continuous data where the function is integrated over a range to find probabilities.
For a function f of x to qualify as a valid probability density function, it must satisfy these three conditions. Number 1. F of x must be greater than or equal to 0 for all integers. This means that PDF cannot have negative values since probabilities are always non-negative. Number 2. F of x must be piecewise continuous. Number 3. The integral of f of x over the entire real number line, that is from negative infinity to positive infinity, must equal to 1. This reflects that the fact that the total probability across all possible outcomes is always 1. The fourth point on the slide highlights the practical application of a PDF. It tells us how to compute the probability that a random variable x lies between two values a and b. This is done by calculating the integral of f of x from a to b, which is a continuous equivalent of summing probabilities for discrete variables.
This is an example of a probability density function. Given that f of x is equal to 0.048x times 5 minus x. A. Verify that f is a probability density function. B. What is the probability that x is greater than 4? C. What is the probability that x is between 1 and 3 inclusive? Let's get started. If f is a probability density function, it has to be equal to or less than 0. So, x has to be between 0 and 5. Now, how can we verify that f is a probability density function? The integral from negative infinity to infinity of any probability density function by definition has to equal 1. And since x has to be between 0 and 5, the integral from 0 to 5 of f of x dx must also equal to 1, so this is what we need to verify. So let's integrate 0.048 times 5 minus x dx from 0 to 5, and let's see if it's equal to 1. So the first thing that I'm going to do is I'm going to move this constant to the front, and then I'm going to distribute x to 5 minus x. So it's going to be 5x minus x squared. Now, the antiderivative of 5x, that's going to be 5x squared over 2, and the antiderivative of x squared is x cubed over 3. So now, let's plug in 5. So 5 squared is 25 times 5. That's 125 over 2. And then 5 to the third is 125 over 3. So using your calculators, 125 over 2 minus 125 over 3 is equal to 125 over 6. This is then multiplied to 0.048, and it results to 6 over 6, which is equal to 1. Therefore, f is indeed a probability density function. Now let's move on to part B. What is the probability that x is greater than 4? So to find a probability that x is between a and b, we need to evaluate the definite integral from a to b of f of x dx to calculate the probability that x is greater than 4, which means that it's between 4 and 5. Now we integrate 4 to 5, 0.048x 5 minus x dx. So using your calculators, you can input this, and this will result to 0.104, or there's a 10.4% chance that x is between 4 and 5, or that x is greater than 4. Now for letter C, what is the probability that x is between 1 and 3? So this is just going to be a definite integral from 1 to 3. This is the same process of letter B, but your function is between 1 and 3. So the integral from 1 to 3, 0.048x times 5 minus x dx, using your calculators, is equal to 0.544. Therefore, there is a 54.4% chance that x is between 1 and 3.
What is cumulative distribution function?
The cumulative distribution function, or the CDF, is a fundamental concept in probability and statistics. It provides a way to describe a probability distribution of a random variable.
The CDF of a random variable x is defined as fx of x is equals to p of x less than or equal to x, where fx of x represent the probability that the random variable x takes on a value less than or equal to x. Assumption: the probability variable x is well defined with a known probability distribution. The probability distribution satisfies the axioms of probability. Hi, in this problem, we'll get some practice working with PDFs and also using PDF to calculate CDF. So the PDF that we're given in this problem is here. So we have a random variable z, which is a continuous random variable. So the first thing we need to do, and the first part of this problem, is we need to figure out what gamma is, because it's not really a fully specified PDF yet. So we need to figure out exactly what the value gamma is. And how do we do that? Well, we've done analogous things before the discrete case. So the tool that we use is that the PDF must integrate to 1. So in the discrete case, the analogy was that the PMF had to sum to 1. So what do we know? We know that when you integrate this PDF from negative infinity to infinity, fz of z, it has to equal 1. Alright, because we know that the PDF is actually only non-zero in the range negative 2 to 1. So instead of integrating from negative infinity to infinity, we'll just integrate from negative 2 to 1. And now, let's plug in this gamma times 1 plus x squared dx. And now, the rest of the problem is just applying calculus and integrating this. So let's just go through that process. So we get z plus 1/3 z cubed from negative 2 to 1. And now, we'll plug in the limits. And that's 1 plus 1/3 minus negative 2 plus 1/3 times negative 2 cubed. And then, we add all this up, which will give you 6. So, gamma is 1/6. Okay, so the next part of the problem asks us to calculate the CDF. So remember that the CDF we use the capital F, and the definition is that you integrate from the negative infinity to this z. And what do you integrate? You integrate the PDF, and I'll use some dummy variable y here in the integration. So what is it really doing? It's basically just taking the PDF and taking everything to the left of it. And another way to think about this is the probability that the random variable less than or equal to some little z. It's just accumulating probability as you go from left to right. So the hardest part about this calculating the CDF really is actually just keeping track of the ranges, because unless the PDF is really simple, you'll have cases where the PDF could be 0 in some ranges and non-zero in other ranges. And then, what you really have to keep track of is where those ranges are and where you actually have non-zero probability. So in this case, we actually break things down into 3 different ranges because this PDF actually looks something like this. So it's non-zero between negative 2 and 1, and it's 0 everywhere else. So then, what that means is that our job is a little simpler because everything to the left of negative 2, the CDF will be 0 because there's no probability density to the left. And then everything to the right of 1 will have accumulated all the probability in the PDF because we know that when you integrate from negative 2